Hello everybody and welcome to the online certification NPTEL online certification course on microelectronics device circuits. This module is combinational logic design module number 4. In our previous modules we have looked into pass transistor logic, we have also looked into transmission gate logic, and we have seen how these logics behave under various signals given to it. What are the relative advantages and disadvantages of each of these logic design. Today in this module we will take up dynamic logic and see how is it different from static logic. As I discussed with you in the initial slides, the very first slides of my combinational logical block, that static logics are those logics which are in which the output is either connected to VDD or to ground or VSS, and therefore it is basically a low impedance node. Whereas when you talk of dynamic logic, you can have a floating node picture available to you. So with this let me come to the first outline of the module, and the outlines of the module are: we will look into dynamic CMOS circuit design, we understand what is the meaning of precharge and evaluation with respect to dynamic CMOS, we look into the properties of dynamic CMOS logic design, dynamic CMOS logic. Then speed and power of dynamic logic. So these are the performance matrix here, right, matrix and matrix, and then we look into the signal integrity issues of a dynamic design. That typically dynamic design has got a major problem of signal integrity, that means there is heavy leakage and so on and so forth. So that is what I was looking in blue, it is marked here, that within this we will be looking into feed through, capacitive coupling, charge sharing and charge leakage. We will try to understand how we can cascade dynamic gates for a performance enhancement, and then looking into domino logic, and then NP CMOS we will look into. This is the final one we will do, and then we will recapitulate finally the whole discussion. So this will be the outline of the whole talk as far as this is concerned. Let us look at the dynamic logic here. An alternate style to remove static power dissipation is called a dynamic CMOS logic design. If you remember at one point of time when we were using CMOS architecture, simple CMOS architecture, and you had NMOS and PMOS as your PUN and PDN, then remember when you are going from 1 to 0 and the output was going from 0 to 1, if you plot the VTC, it comes something like this, right. So if you plot V in versus V out, I get the profiling something like this, right, the profile was something like this. Now, but somewhere in the middle right here, right, effectively both your devices are in the on state for a very short duration of time, and as a result if you plot the current flowing through the both the arms, you will see that this current suddenly peaks here and then falls down. So this is the current and this is the voltage. This peaking, this current is referred to as a short circuit current, right. So this is the short circuit current which you see. So this is the short circuit current which is there with you, and this short circuit current implies that you will always have a large current at certain point of time. Now let us come back to a dynamic logic and see how it is removed. Dynamic logic, you have one single pull up just like a pseudo NMOS inverter PMOS, and you also have a evaluation transistor known as ME. So this is an NMOS, also referred to as an evaluation transistor ME, and this is MP, also known as a precharge transistor. We will explain these terms individually, but we will come to that later on. So and this is the pull down network which you see, this black box is basically pull down network with inputs I1 to IN here, and the output is basically here with this is the load capacitance which you see. Now it is very simple and straightforward. Whenever your clock is equals to 0, right, your ME is switched off, right, and this is switched on. So when this is switched off and this is switched on, output goes to VDD because this is switched on, but your this transistor is not coming into picture at all because this has been cut off. So when your clock equals to 0, right, and this transistor switches on, your output goes to 1. Now when your clock goes to 1, right, then this clock this also goes to 1, right, and therefore this switches off. But then depending on the value of your input vectors I1 to In and the type of logic design which is there in the pull down network, either the output will go to 0 or it will not go to 0. For example, if your pull down network is a something like this, and then this is your ME, this is already on, right. If this both inputs are 1 1, then out which was initially held to 1 will now go to 0 across these transistors, but if your input is 0 here, this will still hold the output equals to 1. You are getting my point. So, two things happens, one is the type of network which you are choosing in the pull down network, that, and the type of input you are choosing here will determine whether output. So, you see at no point of time VDD is directly connected to the ground, and as a result, because you have clock and because you have this driving this clock transistors, as a result you will automatically have much lower short circuit power dissipation. That is what is all written here. And so, that evaluation, for example, when clock equals to 0, out will be precharged to VDD, right, this will go to VDD, the out value will go to VDD, and this will be disabled or this will be switched off, right, pull down network will therefore be disabled. So, this will not work, right, and therefore out will go to VDD. Now, when clock goes to 1, right, MP switches off, right, and based on the values of A, B and C, out will either go to 0 or remain stable. Now, once you have A, B, C, suppose both, say A equals to B equals to 1 and C equals to 0, then out will discharge through this path and out will go to 0, clear. When out goes to 0, we get an important issue here, that you will never be able to recapture or have the value equals to VDD until and unless your clock goes to 0 once again. So, till your clock goes to 0, your output will never go back to VDD. So, in the sense that once out node is discharged, it cannot be charged until the next precharge cycle. You understand this point? And therefore, out can be written as clock bar, because clock bar when it is high, then clock will be low. So, this will be 0, right, and therefore, out will be equals to VDD, out is equal to 1. Similarly, when clock equals to high and clock bar will be low, so this will go to 0, this will go high, and then depending upon A, B and C, out will be determined, right, and this is basically your the complement value will be shown to you. Why? Because if you, for example, if we take 1.1 plus 1, I should get output should be equals to 0, and that can only happen if we have a NOR function or a NAND gate. What is the property of dynamic logic? The construction of PDN is therefore exactly the same as the construction of the PDN is the same as your static CMOS logic. We have already done that. So, PDN network is exactly the same. However, it is much lower than the static CMOS logic. You actually require n plus 2. N plus 2 why? Because n is the number of pull down networks, n plus 2 because one precharge transistor and one evaluation transistor. Of course, it is a non-ratioed logic, right, which means that the sizing of PMOS precharge device is not important for realizing proper functioning of the gate. Please understand, proper functioning means logical function of the gate is not determined by the W by L ratio of the PMOS transistor. PMOS transistor therefore W by L ratio will only help you to precharge your output node to VDD, that is all, right. It does not play a role in determining the VTC, voltage transfer characteristics, in any way, and therefore we define this to be as a non-ratioed. As I discussed with you, it only consumes dynamic power, and therefore the overall power dissipation can be highly compared to static logic gate, because dynamic power is very high, and since you are using clock, its power can be very high. However, these gates have much faster switching speeds because of your reduced load capacitances. Because why? Because now the number, see, in a CMOS inverter you had almost double the number of gates. Here the number of gates have drastically reduced, and therefore your loading of the capacitance actually reduces and the speed of the circuitry improves. So, dynamic circuits are relatively faster in nature, right. Let me come to speed and power dissipation in dynamic logic. The main advantage was, as I discussed with you, increased speed and reduced implementation area because of less number of transistors with you. However, there is a small problem here, that when the input, suppose your input goes high and the clock goes high, then the output should go low, and it goes low also, but the problem is that output going low across say M4, M3, M. So, whenever my clock goes to 1 and this goes to 1, depending on the value of in 1 equals to in 2 equals to in 3 equals to in 4 equals to 1, then only out will actually discharge to this path, which means that the discharging path has got a large resistance being offered, right. So, your delays will be typically large, and therefore, you see your out is basically delayed by a large quantity here, right. And not only that, your out is also showing a small glitch here and a glitch here. So, you have a glitch here and you have a glitch here, this is known as a glitch. This is because of a capacitive coupling, we will see later on as we move forward, but this is because of capacitive coupling, and therefore, you will see suddenly, because the reason this happens is that as the input suddenly increases, there is a capacitive coupling between input here and the output here, right, and as a result the output shows a certain glitch in the output side, and therefore, that increases the capacitance. In a dynamic logic, you do have a problem of charge leakage, and that is very important, or that is very difficult to do that. Ideally, as I discussed with you, your pull down network is off when the output is at VDD. So, when your output is at VDD, right, since your clock is at low voltage, and so this is cut off, right. However, there is a problem. The problem is that there is a so when you precharge it, your output voltage goes to a high value, right, it goes to a high value, but though your ME is switched off, you still have, let us suppose A equals to 1 now, and this transistor was switched on, M1 was switched on. So, any cap here, right, or any reversed bias connected diode here, which is basically the depletion capacitances, the charge will actually leak through these domains, and therefore, the precharge value will start to fall down until and unless the next clock pulse comes and tries to raise the value to a high value. So, you are losing the charge because of leakage, charge leakage, especially in a case when you have signal integrity issues in a dynamic design. So, whenever you have a dynamic design, you do have a problem that your pull down network, though ideally is supposedly switched off, but if let us suppose one of the gates connected to the output node is switched on, then the output node charge might actually go through this particular device, which is the on state device, and reside in its capacitances, say a reversed biased PN junction diode capacitance, or the CL load capacitances, or maybe parasitic capacitances. So, what will happen is that you lose it, and once you lose it, you do not have any other option but to wait for the next precharge cycle to come, right, and so that loss is pretty steep. So, you see it has actually gone down to a larger extent. So, now what happens is that when you go now to the evaluation phase, which is when your clock equals to 1 and clock equals to 1, then you start from here rather than from here. So, you are not able to utilize the whole swing of the design in this case. So, this is one of the problem areas which you see. So, what people thought and people did also, they introduced what is known as a bleeder transistor. Now, let us see how it works out, very simple and straightforward. What I do is I have MA MB, so it is an AND gate, this is my evaluation transistor here, and this is MA input 1, input 2, A and B are inputs here, clock, and I have put a bleeder transistor MB1 here, right. So, let us see how it works out. So, let me say that clock is basically equals to 0, this charges up to a very high value. So, this charges up to a very high value, this is a normally on device because PMOS is connected to ground, and since this is typically high value, so sorry, this becomes a high value, even if these transistors are switched on, if suppose this transistor is switched on, even if some discharge takes place, I still have VDD connectivity here, and the VDD will appear and charge this node once again. So, this node will be again charged to a high value. So, you do not lose charge because you are applying a charge from external world. Similarly, if I take a NOT gate here, and if I put, suppose this is, for example, if I take this to be as equals to 1, right, because it has charge to this value, this will become 0, this will become 0 implies that MB1 will be on, MB1 will be on means that this VDD will be always connected to this particular capacitance, and the capacitance charge will never be lost. You will have always a high capacitance value there, and when my this goes to 0, when this goes to 0, this becomes equals to 1, this cuts off and you enter into the evaluation phase. So, this MB1 is defined as my bleeder transistor. Bleeder means it is basically bleeding the charge from VDD onto the capacitance which you see in front of you. One classic example which you see, one of the classic example is basically to do with I will just discuss with you the classic problem. The classic problem of this thing is that when you have a capacitive coupling between the two, we also have a charge sharing. What does the charge sharing mean? Charge sharing means that whenever your device switches off, the charge which is there within the device has to sit somewhere, right, it has to go somewhere, right, and therefore it will that charge will be shared between 2 or 3 devices and its voltage will go up. I will explain to you how this is worked out. Let us suppose the initial conditions are that my V out equals to VDD and Vx equals to 0, VDD. So, V out is VDD. So, I have already this is VDD, right, and I have already into evaluation phase. Vx which is the voltage at this intermediate point, this is the intermediate point x, Vx equals to 0 because obviously you are switched on, and now what I am doing is I am giving a signal A equals to 0 to 1 and B is stabilizing at 0, right. Now, if del V out is much smaller than threshold voltage of this device, right, del V out means the change in the voltage, gate voltage is smaller, then if this is switched on, this voltage will appear here, it is behaving like a pass transistor logic as VDD minus VTN, right. Now, but if del V out, change in the del V out value is very large and is much larger than the threshold voltage of this MA, then Vx and VDD, these two will reach to the same value and your del V out will be in what is the condition for del V out is VDD upon CA plus CL, like CA is this one and this is CL, right, which means that it is basically a capacitive coupling, and depending on the effective values of CA and CL, my V out will be there. So, if you look at del V out, it is equals to minus VDD. If you divide numerator and denominator by CA, I get 1 by CA upon CA. So, you see if your CL is very large as compared to CA, this quantity will be very large, right, and therefore, this quantity will be very small, right, and yes, so it will be very small and therefore, del V out will be very large. It will be so also because if your CL is very large, the most of the charges will be accumulated at CL and the voltage change at output will be very large. Similarly, if your CA is larger, then CA is larger means this is large, which means that this falls down, and therefore I will just reframe my question, the understanding here. If CL becomes large, then this quantity becomes large, right, and therefore del V out goes down. The reason is that with increasing value of CL, more and more charge will be accumulated here, whereas when you increase the value of CA, the more distribution will take place and your V out, del V out will actually become larger and larger, right. This is known as charge sharing. So, whenever you switch on MA, right, because A goes from 0 to 1, some charge from this VDD node goes on to MA node, and therefore, del V out shows a small drop, right, and this drop is, you see, negative, you see it is negative actually, and as a result you will always see a drop, right, and this is charge sharing phenomena in a domino logic, in a dynamic logic. Let me discuss with you the capacitive coupling therefore. The capacitive so my output impedance is relatively high and therefore it is very sensitive to crosstalk effects. That is the only problem area of a dynamic logic, because this is quite high, Z out is equals to infinity ideally, right. The wire next to the dynamic node may couple capacitively and destroy the floating node, right, and that is a problem area which you face for a dynamic logic design. So, what people did, so this is a bleeder circuit which you see in front of you, and this is a bleeder transistor here which tries to make the level again go to back to VDD. So, even if there is a problem with your output because of charge sharing or because of leakage, this helps you to raise the value to a high value. right. But the problem here is that why is it z equal to infinity is it is behaving like a floating node, because why, because your clock has actually gone to 1, clock is equals to 1, this is switched on, but let us suppose A and B are both 0, then this will be acting as a floating node with high output impedance, right, and therefore they will be all affected by crosstalk noise, and electromagnetic interferences will happen here to a larger extent, right. And this is therefore known as, this will result in externally the signal being getting degraded to a larger extent. The last, let me come to the last problem area of this thing, and this is what is known as a clock feed through. Clock feed through is basically a capacitive coupling between the clock input of the precharge device and the dynamic output node. So if you look back here, this was the clock here and this was the output here. So your clock goes high like this, right. Now because of a coupling between this and this, the node voltage also goes like this. So you see here, when the clock goes high, right, the output should remain stable like this to VDD, but actually it goes beyond VDD for some duration of time and then starts to fall back. This is because of the fact that for a finite duration of time, because you see clock is rising very fast, which means that omega is very large, right. So omega is large means 1 by j omega c is very small, xc. So xc is small means it is looking almost like a transparent medium. So any small change in the clock here, high frequency change, will be easily detected at the output node of my precharge, and that is the reason you will have a voltage, and as a result what happens is that the voltage rises beyond VDD, right, and that results in what is known as a clock feed through, and this results in a larger power dissipation and signal integrity issues. So power dissipation is a problem. Now let us look at cascading of two dynamic gates. So I have cascaded how? So output is cascaded back into the input of the second gate. Now you see, if my clock goes high and my input also goes high, my out 1 will start to fall down. Obviously the input goes high means this is on and the output starts to go down. It starts to go down means this, so it was initially on, this was high, right, it was high. It was high means I should get out to be equals to 1 to 0. Why it is 0? See, initially when your clock is low, right, and input is low, clock is low, input is also low, out 1 will be high, which means that this is on, but then your clock is low and input is low, therefore this will be off, and out 2 will be, so the clock is low means out 2 will be also latched to VDD, that is what is happening here. Now as your input goes high, it takes some finite amount of time to output to fall down, output starts to fall down, as it crosses the threshold voltage of the next transistor, at this stage this goes to off state. Which goes to off state? The next device goes to off state. As it goes to off state, my out then fixes to that same value where it goes to off state. Ideally it should have been here only, you understand, ideally this should be here, because out 1 was initially high and then starts to fall down, but because of finite delay between the two, this transistor will get switched off at certain amount of time, which is threshold voltage of the device, and as a result what will happen is that the out 2 will be latched to a value which is not exactly equal to its initial value, and therefore there will be a del V change here, and I cannot recover it until and unless I come back to the next precharge cycle. So you see out 1 has fallen down, out 1 is falling down. So out 1 when it was initially high, clock is high, and so clock is high and input is also, so if you look at this, concentrate on this part. So when clock is high and input is high, then ME is on, right, and out should actually fall down, and it is falling also, but it should ideally go to a low value, it should go down if you allow this transistor to go to large value, but then out 2 when it crosses the threshold voltage of the second transistor, it cuts off this second transistor and this latches to a value which is not equal to its initial value, right, and therefore you lose. So when you cascade dynamic logic, you end up losing, that is the problematic operation because of the output of each stage, right? And that is the problem. Direct cascading is therefore not a good idea. So what people thought was that since you cannot directly cascade two logics because the logic falls down, and not only that, you will not be able to recover that logic until the next precharge cycle come, we enter into what is known as a domino logic. So I have inputs here of course, and I have a PDN here and a PDN here. I also have a clock and clock bar. So this if you look at it closely, it is exactly the dynamic logic. Similarly this is also a dynamic logic here, right, but they are cascaded by a static inverter, right, and they are cascaded by static inverter. So you see this static inverter will always ensure that if suppose clock is equals to 0, then this will be VDD. So this will be 0, this will be 0 implies that your PDN will be switched off, and therefore if it is switched off and clock equals to 0, this will be actually VDD and output will be equals to 0, right. Now when this input goes all high, let us suppose, and it is an AND gate, clock goes to 1 and clock goes to 1 here, this switches off, this switches on, and this voltage starts to fall, but nothing will happen here until and unless this goes below the switching threshold of this transistor, which will make this goes to 1 and this will go to 1, and therefore then it will switch on my PDN. When the PDN goes high, this goes to 0 and then output becomes equals to 1, right. So by just inserting a static logic here, a static CMOS logic here, I am able to restore the signal integrity issues in a domino logic, right. So the introduction of a static inverter has an advantage that the fan out of the gate is driven by a static inverter, which is obviously a low impedance node, and therefore it increases the noise immunity. So the noise immunity problem is gone. Since each dynamic gate has a static inverter, only non-inverting logic can be implemented, but obvious. Very high speeds can be achieved in this case, and the reason being that TPHL will be approximately equals to 0, high to low will be approximately equals to 0, right. Now the inverter can be used to drive bleeder device to combat leakage and trans distribution. How you can do that? You can add a bleeder transistor here, right, and this bleeder transistor will be added here, and this will be VDD, it will be grounded, right. It will be taken care of in this manner, and therefore you can have a bleeder transistor directly inserted. So charge loss will be taken care of, the charge sharing will be taken care of, and the domino logic gives you a very good idea about this whole charge description. Now so as I discussed with you, therefore a major limitation of domino logic is that only non-inverting logics can be implemented. Like non-inverting logics means those who do not invert the output. So you just need to reorganize your logic function using simple boolean transform. For example, I can do a domino NAND, this would to be a domino NAND, and this to be as a domino NOR, which you can do, and this is your domino NAND NOR operation by putting a bubbled OR gate, right. We will not go details, we will not go into details of this one to a large extent, but simply by choosing appropriate boolean functions you can actually remove the problem of non-inverting logic in a domino function, right. Another way to solve this problem is a differential logic. It is exactly the same as DC VSL, which we have already learned in our initial modules, and this is also known as dual rail domino logic, in which we do I have got a static inverter applied here and a static inverter applied here. I have got a feedback or a feedback resistance applied here. So you have a positive feedback latch here. So when this goes to 0, this switches on this device, and this goes to 1 here. When this goes to 1, this goes to 0 here, and this goes to 1 here. So you have got 0 and 1 coming into picture. Now this is therefore you see AND gate, and this is basically your NAND gate. So you have series connections here, so you have a parallel connection here in this case, right. So once you ensure that this is 0 and 1, these PMOS transistors MF1 and MF2 help you to speed up the logic, right, and helps you to make this go to 0 very fast, go to 1 0 in a fast manner. The advantage here is you get both inverted as well as non-inverted logic, but the disadvantage here is that you require to generate both your input signal and its inverted signal. So both A bar has to be generated, B and B bar has to be generated in this case, right, and that is the problem area for this logic into consideration. Another alternate approach is using NP logic, right. NP logic, what we do is that it is exactly the same as domino logic, only thing is that we have a dynamic logic with clock and clock, and then we drive it with a dynamic logic with clock bar. So whenever your clock is high, so when clock is suppose high, or let us suppose clock is low, so this is low, but then this is high and this is high. So out of all these 4 designs, right, so if it is 0, clock is 0, clock bar equals to 1 means this evaluation transistor will be on and this will be on, this both will be on together, and as a result what will happen is that you will have a direct path between these 2 points provided ME is on, right, provided your input 5 is a high value which you see, right. So, but NP I will like you to go through it in a much more detailed manner from this book actually, and it gives you a very good idea about NP logic design. So, let me recapitulate what we did till now. We looked into the operation of dynamic logic, and we saw that it can be divided into precharge and evaluation. We also looked into charge leakage, charge sharing phenomena of dynamic logic, and we also saw that there is a signal integrity issue in dynamic logic. How to remove it? There are methods of doing it using for removing the by using static CMOS logic. We have seen that, and NP CMOS is an alternative style to cascade the dynamic logic. So, cascading of ordinary dynamic logic is a difficult task. NP logic is one of the solutions to this particular design, right. With this we finish off the dynamic logic case for a combinational logical block. Thank you very much.